So need to find degrees of freedom. So we know how to find degrees of freedom for x. That's straightforward. That's n sub x minus 1. And degrees of freedom for y is just going to be n sub y minus 1. Life is good. Life is easy. Now, how do you find the degrees of freedom for the difference between x and y, right? Well, that, I'll just put diff so that you know it's different. That is actually going to just be the degrees of freedom for x plus the degrees of freedom for y, right? You just add them together. So if we want to unpack this, if you think about double-clicking on this, you'll get that, right? So n sub x minus 1 plus n sub y minus 1. And I'm just putting the parentheses here so you could see the natural groupings, but obviously you could do them in any order because you could just do them straight across because adding and subtracting, you know, they all have the same order of operations. Okay, so that's degrees of freedom. And once you have that, then you could easily find the t, right? Look it up in the back of your book, or you know, you could do it in Excel. And now let's interpret confidence intervals. So now that we have this confidence interval, let's think about how to say what we have found, right? So I'm just going to briefly draw that picture again, because this picture sort of anchors my thinking. So here's our difference of means, right? So when you look at this d, think of it as the difference of two means, right? I guess I could write DOTM, but that would just be too long. And so here, what we found, if we find something like a 95% confidence interval, right? If we found a 95% confidence interval, that means we have found these boundaries. So what do we say? We say something like this. The actual difference of the two means, right? The actual difference. Actual difference between means. Oops. Of the real population, of the population X and Y, right? The real population that they come from should be within this interval, whatever this interval is, 95% of the time. Or something like, we have 95% confidence that the actual difference between means of the population of X and the population of Y should be within this interval. And that really comes from that notion that this is created from the SDOM, right? And remember, the SDOM, the central limit theorem, says that their means are the means of the population, right? And so we're getting the population means drop down to the SDOM, and from the SDOM means we get this. And so because of that, we could actually make a conclusion that goes back to the population, right? It connects back. Okay. So let's think about if 0 is not in between here, right? Because remember, the null hypothesis, when we think about two means, is going to be something like this, that the mu sub x bar minus y bar is going to be equal to 0. This is going to mean that on average, when you subtract these two things, the average is going to be 0. There's going to be no difference on average. And the alternative hypothesis should then be the mean of these differences should not be 0. They're different. If 0 is not within this confidence interval, then we have very little reason to suspect that this would be true, right? We have very little reason to think that this null hypothesis is true. So we could also say that if we don't find 0 in our confidence interval, that we might, in hypothesis testing, be able to also reject the null hypothesis. But we'll get to that later. I just wanted to show you this because the confidence interval here is very, very tightly linked to the hypothesis testing part. They are really like two sides of the same coin. Okay, So that universe is, I think, fairly straightforward. But I feel like I need to cover one other thing because sometimes this is emphasized in some books versus other books. Some teachers emphasize this over other teachers. So I'm going to talk to you about S-pooled, okay? Because this will come up. So one of the things I hope you noticed was that in order to find our estimate of S-DOD, in order to find the S-DOD's sample error, so S-DOD sample error, right? In order to find this, what we did was we took the variance of one SDOM and added that to the variance of the other SDOM and square rooted the whole thing, right? So let me just write that here. So the S sub x bar minus y bar, right, is the square root of one of these standard errors, the variances, plus the variance of the other SDOM, right? So here what we did was we said, well, let's just treat them separately and then combine them together, right? That's what we did. Now, although this is an okay way of doing it, this will just automatically assume, like this, in doing this, we're sort of assuming that they might have different standard deviations, right? That the two different populations might have two different standard deviations. And normally that's a reasonable assumption to make, right? Very few populations have the exact same standard deviation, right? So for the vast majority of time, you could just sort of assume, yeah, probably if you come from two different populations, you probably have two different standard deviations, right? So this is pretty reasonable to do like 90-something% of the time, right? It's the vast majority of time. But this actually isn't as good of an estimate of this value than if you had just used a pooled version of standard deviation. Here's what I mean. Right now we're saying, okay, these guys, you are what we're going to use to create the standard deviation of X. You are going to be what we use to create the standard deviation of Y, right? And just to make that explicit, I'm going to write this out so that you could actually see the variance of X over the, not square root, over n sub x, and the variance of y over n sub y, right? So we use x's to create this guy, we use y's to create that guy, right? And they remain separate. Now, this is going to take a little bit of reasoning. Think back. If you have more data, more n, then your estimate of the population standard deviation is better, right? More data, more accurate, right? So wouldn't it be nice if we took all the guys from the X pool and all the guys from the Y pool and said, hey, let's put you guys all together, and together let's estimate the standard deviation. Wouldn't that be nice? Because then we'll have more data, right? And more data should give us a more accurate estimate of the population, right? Isn't more, right? Well, you can do that, but only in the case that you have reason to think that the population of X has a similar standard deviation to the population of Y. For instance, if you know, if you have a reason to think they're both normally distributed, right? Okay, so let's say something like this. If you have reason to believe that the population X and Y have similar standard deviation, then you can pool samples together. To estimate standard deviation, right? You could pool them together, and that's going to be called S-pool, okay? Now, there's very few populations that you could do this for. One might be something like height of males and females. Height tends to be normally distributed, and we know that. So heights of like Asians and Latinos or something. But there's not a lot of examples that come to mind where you could do this, and that's why some teachers don't emphasize it. But I know that some others do, so that's why I want to definitely go over it. So how do you get S-pool, and where does it come in? Well, here's the thing. In order to find S-pool, what we would do is we would substitute in S-pool for S sub x and S sub y. So instead of two separate estimates of standard deviations, use S-pool. So really you'll be using S-pool squared, right? And so how do we find S-pool squared? So I'll just write this, right? So in order to find S-pool squared, right, what you would do is you would add up all of the sum of squares, right? So the sum of squares of x and sum of squares of y, add them together, and then divide by the sum of all the degrees of freedom. Okay, so if I double click on this, this is what it really means. The sum of squares of x plus the sum of squares of y divided by degrees of freedom x plus degrees of freedom y, right? And so this is what you'll need to do in order to find S-pooled. And then what you would do is substitute in S-pooled for S sub x squared and S sub y squared. So that's the deal. In the examples that are going to follow, I'm not going to use S-pool because, remember, there's very little reason usually to assume that we can use S-pool. But a lot of times you might hear this phrase, assumption of homogeneity of variance. If you could assume that these guys have a similar variance, right? Variance, standard deviation, same thing. Excuse me. If you could assume they have a similar variance, homogeneous variance, then you could use S-pool, right? But for the most part, for the vast majority of time, you cannot assume homogeneous variance. And so because of that, we'll often use this one. However, I should say that some teachers do want you to be able to calculate both, right? So that's the only thing. Finally, I should just say one thing. Usually this works just as well as pooled. It's just that there are some times where you get a little more of a benefit from using this one, right? So if worse comes to worse, and after the statistics class you only remember this one, if that at all, you're pretty good to go.